Welcome to the Explainer. Right now, literally hundreds of miles above your head, there's an invisible network mapping the globe in real time. We're talking about a massive amount of geospatial data pouring in from Earth-observing satellites and ground sensors. Now, this data has incredible potential across the board, but nowhere are the stakes higher than in military surveillance and security management. Today, we're unpacking exactly how these technologies integrate to create total situational awareness on the modern battlefield. We'll track the tech all the way from satellite mapping in orbit right down to autonomous tactical robots on the ground. Let's get into it. To really grasp this immense scale, we have to recognize that the very foundation of global surveillance starts in orbit. Even with spatial resolutions of, say, half a meter to a meter, modern satellite imagery is incredibly potent. I mean, think about what a half-meter resolution actually means for military operations. It means a satellite can look down and definitively distinguish a civilian truck from a military transport vehicle. And because these images are available for practically anywhere on Earth, commanders can map out vast, remote regions and build battle-ready topographic databases without ever deploying a single scout on the ground.
Section 1. The Eye in the Sky, Mapping from Orbit.
To make sense of this modern battlefield, we first need to define the absolute engine driving it all, GeoAI. Simply put, it's the fusion of artificial intelligence with geographic information systems, or GIS, and remote sensing. Without GeoAI, analysts would just be staring at millions of static photos. You'd literally need armies of humans just to scan for subtle changes. But GeoAI steps in as the brain, turning those static images into a dynamic, trackable map. It gives crucial context and spatial relationships to the raw data, so military analysts can automatically detect hidden infrastructure, track unauthorized border crossings, and even forecast where threats might spread before they actually materialize. A great example of this is how deep learning models, specifically UNets, can autonomously extract precise road networks from highly complex rural environments. And they do this while entirely ignoring natural obstacles like trees and shadows. The AI independently recognizes the paths, mapping out the area rapidly and without any human intervention. In a military context, that is a total game changer. It means you can instantly figure out the optimal troop routes through rough terrain, or expose illicit supply chains that someone intentionally tried to hide deep in the wilderness. The big takeaway here is how AI models utilizing fully convolutional neural networks, like those UNets, completely bypass the limits of traditional mapping. Back in the day, older software relied on handcrafted spectral features and basic edge detection, which meant it would easily get confused by a simple shadow, some diverse terrain, or just a passing cloud, totally ruining the map. But modern deep learning architectures, they act way more like a human brain. They learn spatial details automatically, enabling this incredibly precise, pixel-wise semantic segmentation that scales globally, totally regardless of the weather or how complex the landscape is.
Section 2. Autonomous Ground Operations.
So, we've looked at the massive scale of satellites, but what actually happens on the ground? Well, imagine a surveillance drone infiltrating a deep underground hostile bunker. The very second it goes inside, it loses all GPS and satellite connections. But instead of flying blind, it relies on SLAM, simultaneous localization and mapping. This tech allows the system to instantly understand its tactical surroundings without needing any pre-drawn maps or guiding signals. It just uses an onboard camera to record frames in real time, mapping the interior walls while simultaneously figuring out exactly where it is within that newly drawn hostile map. It's fascinating to realize exactly how a machine thinks when it's navigating a foreign, GPS-denied space. As the drone enters a room, it's essentially dropping digital breadcrumbs, plotting 2D keyframes to actively memorize the shape and layout of the space. But at the exact same time, it's firing out a 90-degree sweep of LiDAR rays. Think of LiDAR as an invisible radar, detecting the distance of incoming walls, corners, and potential obstacles in real time, ensuring the drone doesn't just crash straight into a wall while executing its recon mission. Once it has all that sensor data, the system follows a rapid-fire logical progression to actually make tactical decisions. First up, it maps the battlefield into an occupancy grid map. This designates every single tile in its environment as either a safe, free space or a blocked obstacle. Then the A-star search algorithm steps in to play the navigator, calculating the absolute stealthiest, most optimal route to the destination. Finally, deep Q learning kicks in as the motor cortex. It acts as the brain sending precise, microsecond directional commands straight to the vehicle's physical motors.
Section 3. The Data Overload Bottleneck.
Now, integrating all this global intelligence generates a truly staggering volume of high-dimensional data. Agencies are facing severe bottlenecks because an AI's output is really only as reliable as the data and the processing power behind it. The challenges here are massive. You've got the struggle of merging different coordinate systems and file types between allied nations, plus the simple fact that thick cloud cover can still occasionally blind a satellite. But the absolute most critical hurdle? Latency. In a live combat scenario, a delay in real-time threat detection isn't just some annoying technical glitch. It is quite literally a matter of life or death for personnel on the ground. To solve this dangerous data overload, military networks have to perfectly balance their architecture. A great way to think about it is comparing cloud computing to the general's war room. It handles the heavy-duty, centralized processing of vast historical data, which is perfect for mapping out long-term global security trends. But edge computing, that's the soldier in the trench. For immediate split-second tactical decisions, like an autonomous drone needing to dodge incoming fire, the processing has to happen locally, right there on the drone's microchip. This entirely eliminates the latency of sending data all the way back to a remote server.
So we've seen how perfectly these military tools can map hostile environments, predict troop movements, and locate specific targets. But that brings us to a really critical question. What happens when this unprecedented military-grade visibility is turned toward the public?
Section 4. The Privacy Security Paradox.
The absolute forefront of this technology involves what we call GeoAI foundation models. You can think of these models like an omniscient geographic brain. Because they're highly advanced and multimodal, they aren't just looking at static pictures anymore. They're combining huge amounts of spatial data, everything from satellite imagery and cell phone GPS trajectories to public census data into one massive web of intelligence. And sure, while they are brilliant for answering complex geographic questions or predicting national security breaches, they're also silently ingesting highly sensitive information about our daily civilian lives. This dual-use nature presents a really profound ethical tightrope. The exact same cross-modal intelligence that allows authorities to secure a border by cross-referencing thermal imaging with ground patrol data could inadvertently expose a private citizen's daily routine. For example, an AI model designed to locate a hidden facility could easily learn the alignment between an anonymous Street View image and a civilian's social media post. That effectively doxes their exact home address to anyone who queries the system. To responsibly deploy this kind of intelligence, and really to prevent the creation of an inescapable surveillance state, engineers basically have to fight AI with math. They're developing some very stringent privacy-preserving techniques. For instance, they use geomasking to intentionally blur and obscure exact personal coordinates. They enforce differential privacy to track the overall movement of a crowd without ever identifying a single individual inside it. And they rigorously filter malicious prompts, making sure that while the AI understands the geographic environment perfectly for security, it is mathematically restricted from leaking sensitive personal data. So, as our world becomes perfectly, inescapably mapped by AI, how do we harness the power of total visibility without sacrificing our fundamental right to remain unseen? I'll leave you to ponder that final thought as we close out this explainer on the incredible yet perilous frontier of GeoAI. Thanks so much for joining me, and keep exploring.